Today we're going to look at section 6.2. This involves us using something called the sum and difference formulas for cosines and sine. So we're going to refresh our memories because this is going to be an extension on what we have done in Chapter 5, where we were asked in Chapter 5 to evaluate sine of 120 degrees without a calculator. So there were several different ways that we went about doing this in class. One way was if you were very familiar with the unit circle, you were able to recreate the unit circle and then you could very easily evaluate. But for those that were not comfortable with the unit circle or didn't want to take the time to recreate it, what we can do instead is just sketch a quick picture, and that would help us to evaluate. So just another quick refresher about unit circle. Remember, it starts at 0 degrees. If I go counterclockwise, then I'm talking about positive angles. So 90 degrees, 180 degrees, 270 degrees, and then the full circle is 360. So if I'm talking about 120 degrees, hopefully we're all okay with the fact that it has to be in the second quadrant. So this is where 120 degrees is. But then we want to draw a right triangle. So I always drop down a side perpendicular to the x-axis, and then we can identify this reference angle. Because we're dealing with 120, it takes us 60 degrees to get to the 180, so we have a 60-degree reference angle. And so now we just have to remember our properties of a 30, 60, 90 triangle. The side across from 30 is always the smallest side. I always have that be represented as 1. Now, because we're going in the second quadrant and you had to move left to get to the second quadrant, that side has to be negative. The side across from the 60 is the square root of 3. Because we had to move up to get to that 120 degrees, it was a positive side. Our hypotenuse is always the biggest side. It is always positive. So in a 30, 60, 90, it's always double the smallest. So that's why it's positive 2. So then now we can go back to the fact that if I want the sine of 120 degrees, well, SOHCAHTOA, sine is opposite over hypotenuse. The side opposite the reference angle was the square root of 3, and the hypotenuse was 2. So that's why the square root of 3 over 2 is our answer. So with that hopefully coming back to us, my next question to you is, can we evaluate the sine of 285 degrees without a calculator? So if we don't have our unit circle, once again, if we just try to do a quick sketch, 0 degrees, 90 degrees, 180 degrees, 270, and then the full circle is 360. Notice that in this case, 285 is going to fall in the fourth quadrant. And so once again, we're going to sketch a right triangle by drawing a angle perpendicular or side perpendicular to the x-axis. If I want to know what that reference angle is, I know that this little angle is going to be 360 minus 285, and that turns out to be a 75-degree reference angle. So notice that because 75 degrees does not fall into one of our nice special right triangles, it's not 30, 60, 90, it's not 45, 45, 90. In the past, we've always said that no, we are not able to evaluate without a calculator. That's going to change. Now we're going to be able to. So let me talk about how we're going to be able to. We have these formulas called the sum and difference formulas of cosines and sines. So it might be a good idea at this point for you to pause the video and so you can write down these formulas because we're going to be using them in all of our examples. So notice that there are 4 formulas, 2 of them involving cosine, and we're dealing with alpha. Remember, that's one of the Greek letters. Beta, that's another Greek letter. If those 2 are being added, that's the sum of cosines. And so that creates this formula right here, that the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta, that would get us our calculation. And we can do all this without a calculator. And then I can keep going down the list. And as you can see, when it's subtraction with those 2 angles, we end up adding our 2 pieces together. When we're talking about sine, whatever sign is inside. If I'm adding, my formula tells us that we're adding. If I'm subtracting, well, then I'll be subtracting. So hopefully you paused this and you wrote those down. Let's take a look at how we would use these and do some examples. So say I wanted us to find the exact value of each expression. We've got the cosine of 30 degrees plus 45 degrees. Now, if I actually added those angles together, I get 75. That's not a value that's on my unit circle, which is why we have it broken up where the numbers that we're always going to get are numbers that are a part of our unit circle. So because we're talking cosine and we are adding, that's going to be using the formula where we want to subtract the two terms. But notice that alpha and beta, I'm letting alpha be represented as this 30-degree angle, and beta is going to be representing the 45-degree angle. So essentially, if I use that formula, I want the cosine of 30 degrees times the cosine of 45 degrees minus the sine of 30 degrees times the sine of 45 degrees. Now we have angles that we are familiar with. We can think about our unit circle, or we can sketch really quick triangles and we can figure out our measures. So if you didn't have a unit circle, think about a 30-degree angle. That's going to fall in the first quadrant because remember, 0 degrees, 90 degrees. So we have a 30-degree reference angle in the first quadrant. Across from 30 is the smallest side, it's 1. Across from the 60 is the square root of 3. 2 is the hypotenuse. Every side is positive because we're in the first quadrant. So cosine of 30, if I use my triangle, would be adjacent over hypotenuse. I'm going to skip that 45 for a second because I don't have a 45 triangle drawn yet. If I go to the next part of my formula, notice that the sine of 30, I get to use the same triangle. Sine is opposite over hypotenuse. So that would be 1/2. So now I'm going to go and I see, okay, my other angle is a 45-degree angle. So if I think about where that lies, it's going to once again fall within the first quadrant. When you have a 45, 45, 90 triangle, the two sides are the same and they're both congruent. So they're both 1 because they're the shortest. The hypotenuse is the square root of 2. Everything's positive because we're in the first quadrant. So now if I'm thinking cosine, cosine is adjacent over hypotenuse. I'm going to rationalize this. Remember, to rationalize means I want no square root in my denominator. So I'm going to multiply both the top and the bottom by the square root of 2. So really, the cosine of 45 degrees is the square root of 2 over 2. If I look at the sine of 45 degrees using this picture, well, sine is opposite over hypotenuse. It's essentially the same thing. And so that's also then the square root of 2 over 2. Now that I have each of my sines and cosines taken care of, it's just a matter of multiplying fractions and combining like terms. So if I multiply fractions straight across, the square root of 3 times the square root of 2 is the square root of 6. And 2 times 2 is 4. So the square root of 6 over 4 is part of my answer. Minus, when I multiply the second set of fractions straight across, 1 times the square root of 2 is the square root of 2. 2 times 2 is 4. And because they have the same denominator, I'm going to actually combine them together. And so it turns in the square root of 6 minus the square root of 2, and that's all over 4. I can't add those radicals any further. So this would be my exact value for that expression. If I look at the next example, sine of 315 degrees minus 60 degrees. So we're talking about sine and we're talking about subtracting. So if we think about those 4 formulas, this is the formula that we want to look at. Once again, the first number is going to represent alpha. The second number is going to represent beta. These numbers are numbers that are on our unit circle. If I had actually subtracted them, I would get a number that is not on my unit circle. And so that's why it's important not to actually try to subtract those numbers. So if I want to sketch a picture, if I'm talking 315 I got to realize that the full circle is 360. This down here is 270. So I know that I'm dealing with a triangle here in the fourth quadrant. So if I know that this is where the 315 is, this little reference angle right here is going to be a 45-degree angle. Remember, 45, 45, 90, the triangle has the two congruent legs, but in the fourth quadrant, the side going down is negative. The hypotenuse is always positive. It's the square root of 2. So if I know that I want it to be the sine of 315 times the cosine of 60 degrees minus the cosine of 315 degrees times the sine of 60 degrees. Because I have that picture sketched, I'm going to be able to substitute it in for each of the first terms in my problem. So 315 degrees for sine, using this picture, sine is opposite over hypotenuse. We'll notice that it would be -1 over the square root of 2. Just like the last problem, I'm going to rationalize, and that will turn into negative square root of 2 over 2. If I look at cosine of 315, so using my reference angle of 45, cosine is adjacent over hypotenuse, 1 over the square root of 2, rationalize into the square root of 2 over 2. I'm going to sketch a picture of my 60-degree angle. 60 degrees falls in the first quadrant. All sides are positive. Across from the 60 is the square root of 3. One's across from the shortest, or 1 is the shortest side across from the smallest angle. 2 is the hypotenuse. So now I'm going to be able to fill in the 60 degrees. So cosine of 60 adjacent over hypotenuse would be 1/2. And then sine of 60 is opposite over hypotenuse. That's the square root of 3 over 2. Now I have no more sine and cosine because I've replaced them with the ratios that represented them. And now I'm going to multiply straight across. So I'll have negative square root of 2 over 4 minus square root of 6 over 4. And once again, they have the same denominator, so I don't have to worry about combining like terms. I don't have to worry about finding a common denominator. If I look at my numerator, there's no way that I can combine those any further. And so then negative square root of 2 minus the square root of 6 all over 4 would be my answer. So notice those numbers are very similar to the first problem set of numbers, and that's because that's how it should be. Everything is pretty much going to end up being in terms of 1/2, the square root of 3 over 2, the square root of 2 over 2. For right now, that's kind of how it's going to be. It's just a matter of, are things positive, are things negative, depending on what quadrant we fall in. If I look at this next problem, it says to find the exact value for the cosine of 195 degrees. Here's the problem. That's one number, and it is not a part of the unit circle. It's not going to get us a nice triangle that'll allow us to right off the bat go ahead and think about 30, 60, 90, or 45, 45, 90 triangles. Okay, so what we're going to have to do is we're going to have to recreate this and turn it into either a sum or a difference problem. So just a quick reminder, these are my two formulas when I'm talking about cosine. I can either find two angles to add together to get me 195 degrees, or I could subtract two numbers and have them then add or subtract to be 195 degrees. It does not matter which one of those you pick. You just want to be strategic where you pick numbers that are going to be on your unit circle that will then end up getting you that final number of 195. So think about it. If I was to use the addition problem, so the sum, two numbers that add to get me 195 would be 150 degrees. That's a number that's on my unit circle. And 45 degrees. That's also a number that's on my unit circle. So right off the bat, I could go ahead and now plug those numbers in for the alpha and for the beta, and I can go ahead and solve. If you would have rather decided to do a subtraction problem, we could understand that 315 minus 120 that will also get us 195. So we have two options here. Once again, all of these numbers are numbers that are on the unit circle. So it's really up to you and your preference. Whatever the first number that comes in your mind that's easiest to find, go ahead and stick with that. You should still get the same answer at the end. So if I made 150 alpha and 45 beta, let's go ahead and let's plug it into our problem. So because I am dealing with addition, I know that that means I'm going to be subtracting these two terms. All right. So now notice that I have to figure out what 150 degrees is and where that's located. And then same thing with 45. So 150, that's going to fall in the second quadrant between 90 and 180. And hopefully we're okay with the fact that it's a 30-degree reference angle. So across from it would have to be 1, and it's positive because it's going up. We would have a negative square root of 3 for the other side, and 2 is the hypotenuse. So the cosine of this, adjacent over hypotenuse, would be negative root 3 over 2. If I want the sine of 150, we're using this reference angle of 30. Sine is opposite over hypotenuse. I get 1/2. If I'm thinking about a 45-degree angle, that's going to be in the first quadrant, where the legs are the same. The hypotenuse is the square root of 2. Everything's positive. And remember, because the hypotenuse is a radical, we're going to rationalize 1 over the square root of 2 would be the square root of 2 over 2. And that's going to be my answer for both the sine and, I'm sorry, this should have said cosine. Or sorry, that should have said sine. But they're both 45 degrees. Sine and cosine are going to have the same ratio. All right. So now when I multiply straight across, notice that we'll get a negative square root of 6 over 4 minus, we'll have a square root of 2 over 4. So that's why essentially I can just put them together. And this would be my answer. Okay, so I'm going to really quick justify it that had I subtracted instead of added, we should still get the exact same answer. So if I made 315 my alpha and 120 my beta, notice that this time cosine of 315 times cosine of 120. Subtraction means we're adding our terms together. We'll have sine of 315 times the sine of 120. All right, if I'm looking at where is 315 located, well, that's going to be in my fourth quadrant, where our reference angle is a 45-degree angle. So the sides are congruent, but this side has to be negative because it's heading down. We're dealing with the square root of 2 for the hypotenuse. So cosine, if I rationalize it, is positive. But sine of 315, sine is opposite over hypotenuse. That would be negative. 120 is going to be located in the second quadrant. The reference angle would be a 60-degree angle. So across from 60 is the square root of 3. 1 would be negative because I moved to the left. 2 is the hypotenuse. So cosine is adjacent over hypotenuse. That would be negative 1/2. Sine, opposite over hypotenuse, would be the square root of 3 over 2. So notice when I multiply straight across, we'll get negative root 2, and then that would be over 4. Negative times a positive makes that a negative square root of 6. Once again, over 4. That's why I could put it together. And so even though those radicals are flipped around, they're both negative. So essentially we have the same answer. So that's why you don't have to do both ways. You just pick one. You're either adding or you're subtracting, but you're finding numbers that fall in your unit circle. So that allows you to do this. So let's look at one more. And I'm not going to do two different methods. I'm just going to focus on one way. So if I'm talking about the sine of 255, 255 is not a nice number that's on our unit circle that allows us to find a special right triangle right away. we have to think about creating two angles that either add up to 255 or subtract to get us 255. So the first thing that I'm thinking about is usually addition. I think that, okay, well, 210 and 45 degrees, those two add up to 255. And so I'm going to let that be my alpha, this be my beta. That means I'm using the top equation there. So we'll have the sine of 210 times the cosine of 45 degrees plus, then we'll have the cosine of 210 times the sine of 45 degrees. Okay, so where's 210 located? Well, that's going to fall in this third quadrant because it's between 180 and 270. What's my reference angle? Well, if this is 180 and this is 210, that's a difference of 30. So I have a 30-degree reference angle. Across from 30 is the smallest side. It has to be negative. The side across from 60 is the square root of 3. This is also negative. The hypotenuse is always positive. So the sine opposite over hypotenuse would be negative a half. If I jump over to the cosine of 210, adjacent over hypotenuse, that would be the negative square root of 3 over 2. 45 degrees falls in the first quadrant, where all the signs are positive, so 1, 1, and then square root of 2. So remember, sine and cosine will have the same exact ratio, but we will rationalize, and so we get the square root of 2 over 2 for each of those. Now, as we continue to do this, and you're noticing like the exact same numbers, you don't have to show me a sketch. If you already know what it is, I mean, hopefully by now you understand that sine and cosine 45 degrees will always be the square root of 2 over 2. But I'm just continuing to show you just in case we're still trying to catch on. But if you already know how to do it, don't feel like you have to sketch a picture for me. When I multiply straight across, notice that I get negative square root of 2, and it'll be over 4, plus negative times a positive is a negative, and once again, it's all over 4, so that's why I can just make it one big fraction. There's my exact answer. All right, so that is using the sum and difference formulas for cosines and sine. So this is what I'd like you to practice. On page 605, you're going to do problems 13 through 20.